Jocelyn Bell Burnell arrived at the University of Cambridge in the mid-1960s, just as construction was beginning on a new kind of radio telescope. For 2 years, as she worked on her doctorate in astronomy, she helped string wires between wooden poles planted in a field, until 4.5 acres were woven in copper filament and cable. I came of a family that did a lot of sailing, so it wasn't totally alien. Bell Burnell told me recently. I was used to posts and masts and pulleys. By July 1967, the telescope was ready. It resembled a giant metal net. Within a few weeks, its antennae had caught something unusual. Bell Burnell, who analyzed the roughly 700 feet of paper generated each week as galactic radio waves were recorded in inked peaks, noticed a faint signal arriving from one slice of sky. Then it disappeared. In November, she saw it again. By adjusting the speed of the recording device, she determined that the signal came in every 1.34 seconds, a regular beat against the background static of the cosmos. Bell Burnell puzzled with her advisor, Anthony Hewish, about whether it was of this world, an earthly radio station, perhaps, or of another. They gave it the fanciful nickname of LGM-1, for Little Green Men, just before Christmas, on a morning so cold that Bell Burnell had to breathe on the recording equipment to warm it to working temperature. She found a second signal in another part of the sky. This one arrived every 1.25 seconds. Soon after the holidays, she spotted 2 more. Each of the 4 rhythmic waves originated in a different sector of the universe, effectively ruling out actual LGM as the source. The first signal became, instead, CP 1919, CP, for Cambridge pulsars, and 1919, for the star's celestial location in hours and minutes. A new era of cosmology opened. Pulsars are closely related to black holes. Both are born when a massive star runs out of fuel, its outer layers explode in a supernova, and its core collapses. The star's original mass determines what happens next. If the core was more massive than about 3 of Earth's suns, it turns into a black hole. If not, the pressure and density of the collapse, which fuse electrons and protons into neutrons, produce a neutron star. Pulsars, a subset of these dead stars, spin at immense speeds and have powerful magnetic fields that accelerate nearby electrons, lashing them into beams of electromagnetic radiation. Because the stars rotate, those beams, which can be radio waves, gamma or X-rays, or visible light, appear, to a distant observer, to flash on and off. Pulsars are often called cosmic lighthouses. The existence of both neutron stars and black holes was predicted in the 1930s, and the discovery of pulsars, identified as a type of neutron star soon after CP 1919 was reported, suggested that black holes must be out there, too. The first confirmed black hole was reported a few years later. Pulsars meant that a lot of this kind of crazy theory that had been kicking around since Einstein dropped the general theory of relativity on us, that maybe it was real. Stephen Eikenberry, a professor of astronomy at the University of Florida, told me, "Think of it this way, people were asking us to believe in fairies and elves. But then, when you meet an elf, fairies seem like not such a crazy idea, because of their enormous density and precise, clock-like rotation. Pulsars provided a new way to probe space and theory. These 50 years have been amazingly exciting, with a lot of totally unexpected new discoveries in connection with pulsars rolling in." Bell Burnell, currently a visiting professor in physics at the University of Oxford, said, "Even the first pulsar's disappearance, between August and November 1967, supplied useful information. Interference from interstellar material, it turned out, made the radio waves seem to twinkle on and off. At the time this was happening, we didn't know that there was stuff between the stars, let alone that it was turbulent." Bell Burnell said, "That is one of the things that has come out of the discovery of pulsars, more knowledge about the space between the stars. Close observation of a pulsar and the space around it led to the first confirmed exoplanets, planets orbiting other suns, of interest in the search for extraterrestrial life. Pulsars also helped catalyze the hunt for gravitational waves, wrinkles in the substance of space-time. The most recent detection, this fall, recorded the disruption caused by merging neutron stars. Observations underway around the world promise more insights courtesy of pulsars. They turned out to be much more extreme objects than we had imagined could exist." Bell Burnell said, "Because they are extreme, they tell us a lot about the extremes of physics, the extremes of nature. Their extreme mass, for instance, offers scientists a way to better understand Einstein's general theory of relativity. The stronger the gravitational force, the more clear the effects of relativity, Eikenberry said. He is one of many astronomers who hope for the discovery of a pulsar orbiting a black hole, since the tick of the pulsar's clock could perhaps be seen slowing in thrall of a black hole's mass. Pulsars could also reveal information about the feasibility of an interstellar navigation system. Their regular signals could serve as landmarks by which to triangulate a spacecraft's position. Yet, for all they illuminate, pulsars themselves remain shadowy. The detailed physics of their emissions is still not well understood. We are using those flashes of light to tell us all kinds of very cool things, Eikenberry said. But we don't know how those flashes of light actually happen, how pulsars shine. Burnell did not study pulsars after her doctoral work. She performed other astrophysical research, advocated for women in science, and led institutions including, recently, the Royal Society of Edinburgh. Marriage and motherhood led to a peripatetic, part-time academic life and, consequently, an eclectic curriculum vitae, she said. In 1974, Hewish, Burnell's former advisor, was awarded the Nobel Prize in Physics for a discovery that the committee described as of paramount importance to physics and astrophysics. Hewish had a co-recipient, but it wasn't Burnell, a fact that many observers have attributed to her gender. Burnell has repeatedly noted that Nobels do not generally go to graduate students, and that the committee did not know that she was a woman. But many familiar with the story, and with pulsars for ranging legacy, see injustice. It is just such a clear example of the difference for women and anyone who is not on the top, Matthew Stanley, a historian of science at New York University, said. The whole subaltern community suffers in not getting credit for the work that they have done. Burnell's observations during those chilly winter days and nights, signals captured by wires looped across hoary fields, eventually found their way back to the universe that had sent them. In the 70s, NASA launched 4 space probes to explore the outer solar system. Each was outfitted with a map, which used 14 pulsars to identify our sun's relative position in the hope being that an alien might one day encounter the probes and find its way to Earth. It was the first time we were actually thinking that something that could be made by humans could leave the solar system. Keith Gendreau, of NASA's Neutron Star Interior Composition Explorer mission, said. This kind of crystallized the excitement of the time, of real exploration, of going out there. Of the possibility of LGM. Though neutron stars rotate more slowly as they senesce, the maps ought to be decipherable to intelligent life well into the future. It would be a little bit of a math problem, but totally solvable. Gendreau said. The steady beats of the first 4 pulsars have become part of a vast percussive array. More than 2,000 others, superfast, millisecond, pulsars, slow pulsars, solitary pulsars, pulsars living in pairs, have now been found. As Burnell wrote just a few years after her discovery, these incredible stars continue to puzzle, and occasionally to surprise.